Hello everyone, I'm Wei. Let's get started for today's exercise. Uh, Bingo questions. Let's see the bingo questions. What are the components of the GRUs? The dropout is a technique. It's not a gate. It removes the hidden units stochastically and making the training process noise, forcing the network to make correct predictions. So the resulting models will become more robust. Then let's see the gradient clipping. Gradient clipping, which we call the gradient normalization techniques, which is also not a gate. It can scale the gradients at train time to prevent gradients too big or too small. The second question is about how do GRU differ from the traditional RNNs? Yeah, all of these are correct, but for the third statement, it's important to say that the memories in the very early timestamps are less prominent because of the gradient update process, which we will discuss further in exercise 3. Okay, let's have a look at the exercise 2. What's the benefit of the bidirectional RNN over unidirectional RNN? Let's record GBT and BERT, where we said GBT is unidirectional generative models, whereas the BERT is bidirectional models. The difference of them is GBT is able to work on text generation tasks because it predicts every token based on the previous ones, right? But BERT is a bidirectional models, so it make every prediction based on bidirectional context, which is counterintuitive to text generation task, because we don't know the very future context when we are making first token predictions, right? Okay. Let's see the second question. What's the benefit of adding output connections to the RNN? Without output connections, the output YT at timestamp t is chosen independently of other outputs. So we directly compute the probability of YT independently from other outputs. And when using output connections, and we can compute the probability of YT given the previous outputs. Okay, let's have a look at the exercise 3, theoretical background of vanishing gradient. The solutions to the question 1 and question 2, I think it's clear. And let's look at the question 3 based on your findings in question 1 and question 2. Which activation function would you recommend for an MLP with more than 3 hidden layers? What would happen if you choose a less suited activation functions? And suppose we have m hidden layers, and we want to compute the gradients in the first timestamp, and then we will receive a function of sigma prime m times, right? And so, okay, the sigma prime, which means the derivative of an activation function. Okay, so if the activation function, if the sigma prime, or we say if the derivative of an activation function is very small, for example, the derivative of a sigmoid is 0.25, right? So after multiplication of 0.25 m times, the gradient will get the final gradient will get very close to the zero, right? So we call this is gradient vanishing problems because without any prominent gradient signals, the models cannot be updated. Okay. So the recommendation is to just to use an activation function with gradient close to 1, such as ReLU and its variants. Okay, I think that's all for today's exercise. See you next week. Bye.